Dear students, in this video we are going to study about the property of hysteresis. The hysteresis part for B and H, remanence, coercivity, hysteresis laws, hard and soft magnetic materials, applications of hysteresis loop in the making of permanent magnets, electromagnets, and also the core of the transformer. Now let us study about hysteresis. What is meant by this hysteresis? That is the phenomenon of lagging of magnetic induction behind the magnetizing field is called hysteresis. Hysteresis means lagging behind. In this case, this is the hysteresis curve. Here, the magnetic induction lags behind the magnetizing field, and therefore this is called as hysteresis curve. Now let us see what is this phenomenon. When a ferromagnetic material is kept in a magnetizing field, the material gets magnetized by induction. An important characteristic of ferromagnetic material is that the variation of magnetic induction B with the magnetic field H is not linear. Actually, it will be like this. So starting from this point A, it reaches the point C. Next, it comes to the point D, then E, then L. This is the way the material behaves. Then it moves from the point F to the point C, like this. This is for saturation, yeah, and this is saturation in the opposite direction. This means that the ratio B by H is mu, which is equal to mu, is not a constant. Let us study this behavior in detail. Now let us consider a ferromagnetic material, for example iron, is magnetized slowly by a magnetizing field H. Magnetic induction B of a material increases from the point A with the magnitude of the magnetizing field and then attains a saturation level. So from this point A, it attains the saturation level C. This response of the material is depicted by the part AC as shown in this diagram, AC. The saturation magnetization is defined as the maximum point up to which the material can be magnetized by applying the magnetizing field. Then if the magnetizing field is now reduced, the magnetic induction also decreases but does not retrace the original part CA. It takes a different part CD like this. So this is how it travels. And if the magnetic field is now reduced, the magnetic induction also decreases but does not retrace the original part CA. It takes a different path CD. When the magnetic field is 0, the magnetic induction is not 0 and it has a positive value. This implies that some magnetism is left in the specimen even when the magnetism field is H is equal to 0. The residual magnetism AD present in the specimen is called remanence or retentivity. How to define remanence? This remanence is defined as the ability of the materials to retain the magnetism in them even after the magnetism field disappears. So in order to demagnetize the material, the magnetism field is gradually increased in the reverse direction. Now, the magnetic induction decreases along DE and becomes 0 at E. The magnetism field AE in the reverse direction is required to bring the residual magnetism to 0. The magnitude of the reverse magnetizing field for which the residual magnetism of the material vanishes is called its coercivity. Further increase in H in the reverse direction causes the magnetic induction to increase along EF until it reaches saturation at F in the reverse direction. If magnetism field is decreased and then increased with the direction reversed, the magnetic induction traces a path FGKC. This closed curve ACDEF GKC is called hysteresis loop and it corresponds to one cycle of magnetization. So in the entire cycle, the magnetic induction B lags behind the magnetizing field H. This phenomenon of lagging of magnetic induction behind the magnetic field is called hysteresis, and hysteresis means lagging behind. So what is hysteresis law? During the magnetization of a specimen through a cycle, There is a loss of energy in the form of heat. This loss is attributed to the rotation and orientation of molecular magnets in various directions. It is found that the energy loss or dissipated per unit volume of the material when it is carried through one cycle of magnetization is equal to the area of a hysteresis loop. Based on the shape and size of the hysteresis loop, the ferromagnetic materials are classified into hard and soft magnetic materials. The soft magnetic materials have smaller area and the hard magnetic materials will have a larger area. The comparison of hysteresis loops for two magnetic materials is shown in this figure, and properties of soft and iron magnetic materials. Soft and hard magnetic materials are compared in the table 3.2 here. Now let us see what are the applications of this hysteresis loop. The significance of hysteresis loop is that it provides information such as retentivity, coercivity, permeability, susceptibility, and energy loss during one cycle of magnetization for each ferromagnetic material. Therefore, the study of hysteresis loop will help us in selecting proper and suitable material for a given purpose. Permanent magnets, the making of permanent magnets. The materials with high retentivity, high coercivity, and low permeability are suitable for making permanent magnets. Examples: carbon, steel, and alnico. Electromagnets. The materials with high initial permeability, low retentivity, low coercivity, and thin hysteresis loop with smaller area are preferred to make electromagnets, as they have to be magnetized and demagnetized very often. The examples for these are soft iron and mu metal, that is nickel ion alloy. Next one is how to make the core of a transformer. The materials with high initial permeability, large magnetic induction, and thin hysteresis loop with smaller area are needed to design transformer cores, as the materials will be magnetized and demagnetized according to the alternating current passing through the wire.